We begin our discussion of section 3.5, the fundamental theorem of arithmetic. What is the fundamental theorem of arithmetic? Here it is. Theorem 3. The fundamental theorem of arithmetic says the following. Suppose A is an integer number which is greater or equal to 2. Let us consider factorizations of A. P1 times and so on Pm and Q1 times and so on Qn, where P's and Q's are prime numbers. The fundamental theorem of arithmetic says the following. M is equal to N, and Q's can be reindexed, so then Qi is equal to Pi for all i's. In simple words, factorization of an integer greater or equal to 2 is unique up to the order of terms. Now, some people say that the fundamental theorem of arithmetic is kind of obvious because we cannot write an integer into fundamentally different ways as the product of prime numbers. However, this is actually a highly non-trivial fact. Here is why. Please take a look at the following example. Note that there are distinct integers n1, n2, n3, and 4 such that n1 times n2 is equal to n3 times n4. For example, 1 times 6 is equal to 2 times 3. n1 is 1, n2 is 6, n1 times n2 is equal to n3 times n4. However, there are no distinct prime numbers P1, P2, P3, P4 such that P1, P2 is equal to P3, P4. So, there are distinct integers such that this is true, but there are no distinct prime numbers such that this is true. To make this fact even more non-trivial, let us go back to elementary school. Let us think about what is multiplication. So, according to what is written here, there are distinct integers n1, n2, n3, and 4, such that n1 plus n1 plus and so on plus n1 n2 times is equal to n3 plus n3 plus and so on plus n3 and 4 times. But there are no prime numbers such that P1 plus and so on plus P1, P2 times is equal to P3 plus and so on plus P3, P4 times. And now, looking at this, what is written here is a highly non-trivial result. Why this is possible? But if we impose an extra condition, namely, if these integers are distinct prime numbers, this is impossible. How to explain it? Why is that?
I don't know if we've proven this yet or if we could assume it, but it's because if you have a product of two integers, then that product has factors which are the factors of the two integers.
And why is that?
Mm,
Once again, note that this number is divisible by n3, it is divisible by n4, also it is divisible by n1 and n2. However, this number is divisible by p3, it is divisible by p4, but it is not divisible by p1 and it is not divisible by p2. Why is that?
Professor,
Yes.
we can prove it using Euclid's lemma.
What do you mean by Euclid's lemma?
So if prime p divides the product of AB of two integers product AB, then prime p must at least divide one of those integers.
Wonderful. You are talking about theorem 1. Is this what you are talking about?
Yes.
So guys, indeed, in order to prove the fundamental theorem of arithmetic, we need a bunch of theorems. And theorem number 1 is the following. Suppose A, B, and C are positive integers such that A and B are relatively prime. Suppose also A divides BC, then A divides C. Note that if we skip this condition, what is written here is not true. And here is a control example. Please take a look at this. Note that 6 divides the product, but 6 does not divide 2 and 6 does not divide 3. So if we skip this condition, and indeed over here 6 is not a relatively prime with 2, 6 is not a relatively prime with 3. If we skip this condition, this conclusion is not necessarily true. Sometimes A divides BC, but A does not divide B, and A does not divide C. However, if A and B are relatively prime, and if A divides BC, then A divides C. Now let us prove it. Let us go back to theorem 2 from section 3.3. By theorem 2, the greatest common divisor of A and B can be written as their integer linear combination. Note that since A and B are relatively prime, the greatest common divisor is equal to 1. So, by theorem 2, the greatest common divisor can be written as an integer linear combination of A and B, but the greatest common divisor is equal to 1. So, there are integers S and T such that SA plus TB is equal to 1. Here is what we do next. Let us multiply both sides here by C. If we multiply both sides here by C, we get this. Since A divides BC, A divides TBC. This term is also divisible by A. Since both terms are divisible by A, their sum is divisible by A. Now we use theorem 2 from section 1.5. So the left-hand side is divisible by A, therefore the right-hand side is divisible by A. It's exactly what we wanted to prove. Repeat once again. Step 1. The greatest common divisor is equal to 1. By theorem 2 from section 3.3, the greatest common divisor can be written as an integer linear combination of A and B. But the greatest common divisor is 1. So 1 can be written as an integer linear combination of A and B. Multiply both sides by C. Done. This term is divisible by A. Since BC is divisible by A, according to what is written here, TBC is divisible by A. So this is divisible by A, this is divisible by A. Therefore, by theorem 2 from section 1.5, the whole left-hand side is divisible by A. Since the left-hand side is equal to the right-hand side is divisible by A. C is divisible by A. This is exactly what we need.
Sorry, Professor, just to clarify, A and B only have to be co-prime. They don't actually have to be prime, right?
Yes, exactly.
Yeah, okay.
Note that when we say numbers are relatively prime, this does not necessarily mean that A and B are prime. Here is an example. Note that 9 is not a prime number. 4 is not a prime number, but 4 and 9 are relatively prime numbers. When we say relatively prime, this means the following. A and B do not have a positive divisor greater than 1.
Okay, thanks so much.
Other questions?
Could you clarify how this proves that a product of two primes cannot equal the product of two distinct primes?
Very good question. Yes, we can use theorem 1 in order to show that this is impossible. Here is how. Note that if there are distinct prime numbers, P1 and so on, P4, such that P1, P2 is equal to P3, P4, P3, P4 is divisible by P1. Since P3, P4 is divisible by P1, so we have this. Think about B as about P3 and C as about P4 and A as about P1. P1 divides P3, P4 according to what is written here. On the other hand, P1 and P3 are relatively prime because P1 and P3 are prime numbers. Moreover, these are distinct prime numbers. Since P1 divides P3, P4, and since P1, P3 are relatively prime, by theorem 1, P1 divides P4. This is impossible because P1 and P4 are distinct prime numbers. We're done.
Nice. Thanks.
So theorem 1 is actually a really powerful result. The proof is short, but note that when we prove it, we make two references on theorem 2 from section 1.5 and on theorem 2 from section 3.3. And let me also remind you that in order to prove theorem 2 from section 3.3, we use the division algorithm. And the proof of the division algorithm, it's over here. The proof of the division algorithm is actually pretty long. So don't be fooled by this short proof. If we expand this and expand this, the proof of this result is actually pretty long. Next. So we discussed one application of Theorem 1. This result. This is impossible. But now let us go back to irrationality of square root of 2. Let me remind you that we already proved that square root of 2 is irrational. Here is the proof. We used the well-ordering property, and the proof was not short at all. However, we can prove that square root of 2 is irrational much shorter. Please take a look at this. We just see this proof is significantly shorter than this proof. It's over here. It's 1 page long. Here we have just few sentences. Sentence number 1, number 2, number 3, 4, 5 sentences long. We are about to discuss this proof. However, before we discuss this proof, let me give you yet another proof of the fact that square root of 2 is irrational. I give proof 2, this will be proof 3. I give proof 2 in order to help you appreciate this relatively short proof even better. So guys, if you Google irrationality square root of 2 in most sources, the default proof is this proof. Let us go over. So, as before, we assume to the contrary that square root of 2 is rational. Rational means the following. Square root of 2 is a divided by b, where a and b are integers. Moreover, the denominator is not equal to 0. Now, in proof 2, sentence number 2 is the following. Without loss of generality, we can assume that a and b are positive integers. To the contrast, in proof 2, sentence number 2 is the following. Without loss of generality, we can assume that a and b have no common divisor greater than 1. And now the question is, how come that without loss of generality, we can assume that a and b are relatively prime? Well, guys, please take a look at the following. Suppose square root of 2 is equal to a over b, and suppose a and b have a common divisor. Let us denote it by k1, which is greater than 1. Common divisor means the following. A, which is over here, is equal to a1 times k1, and b is equal to b1 times k1, where, of course, a1 and b1 are integers. So, let us copy this over here, and then I'll replace a by this expression and b by this expression. We get this. Obviously, k1 a common divisor can be cancelled. We get A1 over B1. So if square root of 2 is equal to A over B, square root of 2 is also equal to A1 over B1. Now, if A1 and B1 also have a common divisor, let us denote it by K2. K2 also can be cancelled. And we get the following. Square root of 2 is equal to A over B, which is equal to A1 over B1, which is equal to A2 over B2, and so on. Let us cancel common divisors until at some point top and bottom do not have common divisors. Let us denote such a top and such a bottom by AI and BI. Conclusion. If square root of 2 can be written as integer over integer, square root of 2 can be written as integer over integer where top and bottom have no common divisor. Therefore, let us assume from the very beginning that top and bottom do not have common divisor. Once again, in short, if square root of 2 is equal to integer over integer, and these two integers have a common divisor, cancel it out. Here is what we do next. Let us square both sides here. Done. Let us multiply the left-hand side and the right-hand side by b squared. B squared is gone on the right. What is left is a squared. And the left-hand side becomes 2b squared. Observe that 2b squared is divisible by 2 because it is of the form 2 times integer. Since the left-hand side is divisible by 2 and the left-hand side is equal to the right-hand side, the right-hand side is divisible by 2. Now, we will prove in a moment a lemma that says the following. If a square is divisible by 2, then a is divisible by 2. Since a is divisible by 2, a can be written as 2 times k, where k is some integer. And now let us replace a over here by 2k. Done. 2k squared is 4 times k squared. We expand parentheses. And lastly, let us cancel out 2. Done. Now, let us apply same logic as before. The right-hand side is of the form 2 times integer. Therefore, the right-hand side is divisible by 2. But the right-hand side is equal to the left-hand side. Since the right-hand side is divisible by 2, the left-hand side is divisible by 2. But by the same lemma, b is divisible by 2, since b squared is divisible by 2. We get a contradiction. Why? According to what is written here, a is divisible by 2. According to what is written here, b is divisible by 2. But from the very beginning, we assumed that a and b have no common divisor greater than 1. So, we assumed, to the contrary, that square root of 2 is rational, we got a contradiction, therefore square root of 2 is irrational. Now, here is how we prove the lemma. So, we want to prove that for all integers n, if n squared is divisible by 2, then n is divisible by 2. We will prove it by contradiction. Assume to the contrary that there exists an integer number n such that n squared is divisible by 2, such that this is true, but n is not divisible by 2. Since n is not divisible by 2, by the division algorithm, n is equal to 2k plus 1. Here is why we need division algorithm here. Note that by the division algorithm, and actually let me go back to the division algorithm. Note that by the division algorithm, if b is equal to 2, if we divide a by 2, there are only two possibilities for the remainder. A remainder is either 0 or 1. Since here we say that n is not divisible by 2, a remainder cannot be 0. Conclusion, the remainder is 1. Basically, this is exactly what we are talking about here. Thanks to the division algorithm, for any integer n, there are only two possibilities. It is of the form 2q, it is either divisible by 2, or of the form 2q plus 1, it is not divisible by 2. Since here we say it is not divisible by 2, it is of the form 2k plus 1. And now, let us square this number. N squared is equal to 2k plus 1 squared. We expand parentheses. 2k squared is 4k squared. 1 squared is 1. And finally, the middle term, 2 times 2k times 1, which is 4k. Next, let us factor out 2 over here. Done. And lastly, let us replace this term 2k squared plus 2k by m. Since k is an integer number, m is an integer. Conclusion, n squared is of the form 2 times integer plus 1. Since the remainder is 1, n squared is not divisible by 2. We got a contradiction. Here it's written n squared is divisible by 2. Here it's written n squared is not divisible by 2. We got a contradiction which proves the whole lemma. All right, guys. So we discussed two totally different proofs of this theorem. One proof is a page long. The other proof is almost a page long. Now, please take a look at this proof. Only 5 sentences. However, in order to come up with this proof, we use Theorem 1, which is a really powerful result. So, sentence number 1 and sentence number 2 here are same as sentence number 1 here and sentence number 2 here. So, as before, we assume to the contrary that square root of 2 is a rational number. Without loss of generality, we assume that a and b are relatively prime. Also, as before, we square both sides here, done, and multiply both sides here by b squared. Done. So once again, this portion is a copy of this. However, this sentence is different from this. Note that over here we observe that the left-hand side is divisible by 2. Since left-hand side is divisible by 2, or right-hand side is divisible by 2. However, note that the left-hand side is also divisible by b, because 2b squared can be written as b times integer. This is exactly what we use here. The left-hand side, which is written over here, is divisible by b. Since the left-hand side is equal to the right-hand side is also divisible by b. But now let us use Theorem 1 above. Observe that a squared is equal to a times a. So b divides a times a, and b and a are relatively prime. So once again, over here it's a little bit confusing. We have a different choice of a's, b's, and c's here and here. In Theorem 1, we start with the following. Suppose a divides the product of two integers, and a is a relatively prime with one of these integers. Then a divides the other integer. It's exactly what we have here. b divides the product of two integers, a and a. b is relatively prime with a. Therefore, b divides a by Theorem 1. In other words, if over here b and c are equal, as a corollary from Theorem 1, we get the following. If a divides b squared, and a and b are relatively prime, a divides b. It's exactly what we have here. If b divides a squared and a and b are relatively prime, b divides a. Since b divides a divided by b is an integer. It gives us a contradiction. Square root of 2 is not an integer. Done. Folks, any questions here?
Don't we get a contradiction from so after applying Theorem 1, b divides a. So wouldn't we not even need a divided by b, being an integer, but because we already know that b divides a, but we assume that the greatest common divisor between a and b is 1?
No, because we've never said that b is not equal to 1. b is not equal to 0. Indeed, if b divides a, the greatest common divisor is b. But where is the contradiction?
Okay, I think I see now. All right.
You see it now? So this is the fastest way to get a contradiction. Since b divides a over b is an integer. But we know that square root of 2 is greater than 1 and lesser than 2. So square root of 2 is not an integer. We got a contradiction. See it?
Yes.
Corollary. Suppose A, B, and C are positive integers such that both A and B divide C. Suppose also A and B are relatively prime. Then their product divides C. So here's how we prove it. A divides C. By definition of divisibility, C is A times an integer. B divides C. However, C is equal to AM. So if you replace C by AM, we get the following. B divides AM. But note that according to what is written here, B and A are relatively prime. Since B divides the product and B and A are relatively prime, by theorem 1, B divides M. But now again, by definition of divisibility, B divides M means the following. M is equal to B times some integer. Now let us put pieces together. According to what is written here, C is equal to AM. According to what is written here, M is equal to Bn. Now, over here, let us replace this M by Bn. If we replace M by Bn, we get the following. C is equal to A times Bn. It's exactly what is written here. But this, by definition of divisibility, means C is divisible by AB. It's exactly what is written here.